appropriate technique? By parts, definitely. Then it'd be a quick and easy use of, wouldn't it? You mean cheapers. So is it okay if I stop? Yes, Miriam?
So, if all we did right was set it up, how many points are we getting?
Because this really is a question on the integration text, maybe no more than a couple. I'm sorry. But I can make it up to you this week in a few more posts. They're already tied. I'll post them today. Yes, sir.
We're supposed to try and separate y, yeah.
Well, you're supposed to separate variables, meaning bring all the y to the left-hand side, all the x's to the right-hand side. I've already accomplished that at this stage of the game, my second step.
So,
What did you mean by that? Maybe I misunderstood your question.
Like at the end I had like a negative ln cosecant plus cotangent.
Oh, I see your point. I think this one, I think it's going to be nasty enough to where we would solve for y in terms of x, I think. Yeah. Just because you solve a DE doesn't mean you have to explicitly express y. I want you to, if it's easy and it looks nice. Even if you can and it doesn't look nice, I would do it. And there's certainly going to be many examples where it's not possible for you to explicitly express y in terms of x. And you're going to have to just treat it as an implicit solution.
Okay.
Yes, don't get hung up on that.
So I did, yeah.
so
Yeah.
why exactly did you throw the variable z in there and you didn't just call it?
Here's why.
Yeah.
I thought Bradley, I'm being honest.
Okay.
When you look at the original question, it sounded so clunky when I tried to type it. The rate at which y changes back to x is jointly proportional to the square root of the sum of y squared plus y and the tangent of x. And so I just said, well, let me just call it another name. But I'm talking about dy dx, so that means you really need to rewrite that in terms of
Yeah,
x.
okay.
How many? Yes.
Just a side note, on the exam, can you use indirectly instead of inversely for when you
Yeah, I use those words interchangeably.
confused on I wrote 1 over tangent x.
Oh, I see. Because I think I would have to say is inversely proportional to.
Yeah.
I think that prefix or that modifier would have been in front of the word proportional if I really meant reciprocation.
Okay.
Sorry. Didn't mean to be confusing.
But it can be proportional to z and inversely proportional to x at the same time.
Yeah, but since the language is clunky, you know what I would have said? I would have said I'm jointly proportional to z and the inverse of x. And I think that would have been clear that your dy dx would have been equal to my k times my z times my 1 over x. And that's how I get around the phrasing without putting the word inverse in front of proportional, because this was not inverted, the z was not inverted.
Okay.
And of course here, you'd want to replace the z with whatever it is in terms of y. Anybody else want to talk about this or get rid of it before I close it out? Do you guys agree this would be at the level of complexity for Tuesday's exam? Or today's exam, really? Because it involves integration techniques that we have in our past. Okay, I'll get rid of it if you're going to look at me like that. And if you guys don't mind,
So when exactly is it, should you use the comparison test as opposed to the limit comparison test?
always. No. So you guys, here's a good question. I gave you an infinite series. I'm merely asking a simple question, yes or no response. Does that series converge? And I think, because this kind of looks like a 1 over n, I think it might be really convenient just for you and I to compare the nth term of my particular series to the nth term of a series with which I'm familiar, like the harmonic one, 1 over n. So you guys hear me? Algebra, basic algebra. I want to take a peek at 1 over n plus root n, and I'm going to compare it algebraically speaking to 1 over n, but I need to see what that comparison is. So here I go. These two fractions have the same numerators. But this denominator is larger than that denominator. Given that they have the same numerators, though, doesn't that mean the one with the larger denominator is a smaller fraction? Yes. So would the direction of inequality be in that direction? Do you guys agree?
Yeah.
That being the case, you check out what tech I'm really doing. I'm comparing the nth term of my particular series to the nth term of another series with which I'm familiar. And by the way, this is the nth term of the harmonic series, and the harmonic series diverges. So what the heck does a comparison test say?
It says the other one diverges.
I think it says nothing, because my n term is less than or equal to the n term of a series that diverges, which means my series could diverge or converge. I don't know. But cheapers, you guys, the inequality for the reverse direction, I can say a lot, and so I'm pounding my fist on my table saying I'm so darn close to answering the question. Since I'm down so darn close, sorry for my silly choice of words, that kind of suggests that maybe I want to come in and take a peek at the limit comparison test. And I think the limit comparison test would say the following. Let me jump over here. With the limit comparison test, I will take the limit as an increase that bound of the ratio of the nth term of my series to the nth term, of the harmonic series, and just see what the heck I get. Now, manipulating algebraically speaking, that gives me, well, I don't know, cleaning up. Is that an n over n plus root n? Be honest, you guys. Can we do this all in our heads? Okay, that was being honest. I guess not. I guess it's a
Yeah,
this
we
limit.
can. Maybe.
I heard the 1, and I agree with the 1. Not rewriting in terms of continuous function, not employing L'Hopital's rule. Can I just be lazy and do this? But that just gives me this. It's just that now when I allow to increase the n with 2, increase that down, I get that. But I think this just simply evaluates a positive 1. Oh, which by the way is strictly greater than 0. Therefore, by the limit comparison test, since this series right here diverges as the harmonic series, then my particular series, I forget what it was this? Converges as well. Bradley, is that a good enough example? You see where I came so close to using a comparison test? And the reason why I wasted my time to try the comparison test, because it's so easy and quick
So,
and fast.
so why does one converge and the other diverges? That's
I
kinda
have
weird.
no idea. I
Oh.
know my limit comparison
Okay.
test. I meant mine diverges as well.
Okay.
Don't listen to me. So with the limit comparison test, if the limit of that ratio evaluates to anything that's strictly positive, but not infinity, in other words, it evaluates to a non-zero finite real value, then both these series do the same thing.
So you're not supposed to check if the original series diverges. You're supposed to figure that out from the answer if you're comparing it to something that.
That would be begging
Okay,
the
okay.
question, because the original question is, do I converge or diverge with my original
All right.
series?
Yeah, I was just having a problem with the way that was written.
Can you show us a complicated example where you use the comparison test? Because you said that the comparison test is a fairly simple way to do things. Is there like a complicated example that would show up on a test?
In using the comparison test.
Yeah.
I'm not trying to be redundant, I'm not. But I think in terms of the comparison test, I think that was a pretty sophisticated one you and I had the other day. I think that was pretty slick, so I had to think about it. But we've already done that. A sophisticated comparison test.
I don't wanna be wrongly thinking that, comparison tests are all easy.
Now, hold on, don't write this yet. Yeah, it does. I'm sorry, so slow. And I'm getting nervous again. I'm trying to make up an example. I don't know if this is at the level of complexity you're thinking. But I mean, could you guys look at that and apply the comparison test? Did you guys see I cheated, by the way? I said n starts at 2 instead of 1 because at n equals 1 my denominator is undefined. I finagled a little bit. No, I'm asking an honest question. Is this a decent application for this comparison test?
Yes.
Let's give it a shot. Let's take a peek at our nth term. Let's say you and I mess around with the denominator first. Let's keep the numerator the same. Because if I keep the numerator the same, at least I can compare denominators. And I only compare this denominator to one that's simplified. Not much junk in it. Like, how about maybe just something this clean? Given that my numerator is the same, is it not true that this denominator is larger than this one? But if this denominator is larger than that one, doesn't that make this fraction smaller than this one, so the numerator is the same? So is it not true that this is the direction of inequality, or strict inequality? It's fine too. However, you guys, I don't think this answers the question. I don't want to talk about the convergence or divergence of this nth term of a sequence I'm comparing to, because I just think it looks like a mess. Is there any way I can clean this up?
Do you compare the highest power on top and highest power on bottom?
I don't know. Tell me if it's legal. Yeah, is this legal?
It simplifies it when we're in the second.
Well, I know. Before you go there, though, is that legal? I mean, is this inequality a true relation between these two expressions?
I don't think it is, because it would have to be the same power, right?
All right, do this then, David. These denominators are the same, so don't look at them. But I think since n's positive, I'm adding more terms up here, so I think this fraction is bigger than this one, because I'm now looking at numerators, not denominators. I think it's correct. Oh, but as you guys suggested, I do think this one fraction reduces quite nicely down to 1 over n squared. But now wait a minute, wait. Let's back up. Here's the nth term of series that converges as the p series with n equal to 2, where 2 is greater than 1. Therefore, this is the nth term of the series that converges. Excuse me. But my term is greater than the nth term of series that converges, which means what by the comparison test? I can't hear you. Nothing. I think the comparison test doesn't apply in this particular example, because the direction of inequality is all wrong. But it was a good example. How would you change the example so it does work? You're the professor, you're the test writer. How would you change it? Say it one more time. I wasn't even thinking that. You're right. You can change this to n cubed, and then it would work, wouldn't it? Because now if this were, can I change it? Now if this were an n cubed, I wasn't thinking this, by the way, when I asked that question. Now that this is n cubed, I think this reduces down to 1 over n, but this is the nth term of a series that diverges as a harmonic series, or maybe said it diverges as a p series with p being equal to 1, which is not strictly bigger than 1. However, my nth term is at least as big as that nth term, therefore my series diverges as well by the comparison test. I was thinking you guys were going to say this. Rewrite your example so that we're looking at the series involving n squared plus, help me with this, did you do that? Plus 1 over n to the 4th minus 1? I was thinking you were going to say, change signs. After all, this is now the case that my nth term compares to the nth term of a series with this in its nth term's position. Not that. I meant this. But wait a minute. These numerators are the same, but this denominator is larger than that one, which means this fraction is going to be smaller than this one. However, I think in comparing to n squared over n to the 4th, this numerator is smaller than this one, but the denominator is the same, so here's a direction of inequality. But this reduces down to 1 over n squared. Therefore, my nth term is less than or equal to the nth term of another series that converges as a p series with p equals 2, which is bigger than 1. Therefore, by the comparison test, I guess my series converges as well.
Didn't you just change the problem now?
That's what I'm saying. I changed it twice. There's the first one. Here's my second question. So I changed it to this. And now I've asked the third question. Does this series converge? I'm just trying to give an example of these. So 3 examples. Better? Yes, Mary?
I'm sorry,
That's okay.
I did miss this, so I don't wanna make you repeat yourself, but if they both converge, do they converge the same thing?
Ooh, what a good question. As a matter of fact, with all the tests I'm going to give you today, and maybe the integral test I gave you last time, they don't determine what I converge to. They only tell me that I do converge. So this is a big deal, you guys. If I ask you on a test situation, oh, what does the series converge to? You better expect it's going to be either
Telescoping or
a
geometry?
telescoping or geometric series. Now, if you take a peek at all the other tests for convergence, they really amount to do I or do I not converge. They don't tell me what I converge to. That's a big deal. Yes, sir.
So if we use one of those tests, can we find a way, or can we find the limit of that series that we just tested, like using integral or comparison or something?
What do you mean limit?
Like these tell us, like you just said, that a series converges or diverges, right?
Yes.
Can we find the limit of that convergency if,
Do you mean this? Do you mean if I only use a finite number of terms, can I determine how close I am to the real thing?
yeah.
Yes. In a variety of ways. For those of you reading ahead, when it comes to an alternating series, I promise we'll go through it today. When it comes to an alternating series, it's the first n terms is accurate enough to the real value as the absolute value of the first unused term.
What do you mean by unused?
If I use the first n terms in an alternating series, then that is as close to the real value of the actual infinite series as the first unused term. In other words, the n plus first term
Okay.
in absolute values, which is really cool stuff. For you and I looking at transcendental functions on Monday, that's going to be a big deal because I see how accurate I am. Now, if it's not an alternating series, don't worry. I've got another technique as long as I can represent something called a scalar polynomial. I can still get an upper bound on the error I have in using the first n term. It doesn't tell me what the exact infinite series is in terms of the number, but it tells me an upper bound for how far off I am. And that's really cool. Because again, like I told you guys, in mathematics, who the heck cares about approximation techniques unless you know exactly how, not exactly, unless you know how accurate they are. Sorry.
So, before you changed this problem, it was n to the 4th on the bottom. Did we ever solve that one, or?
Yes, we did. No, we didn't. My apologies. We said the comparison test is inconclusive. I was simply addressing someone's question.
Okay, so can we say, is it inconclusive for all numbers we put on the right-hand side, or is it inconclusive just for the
All numbers
1
on the
over?
right-hand side.
I mean, is it inconclusive for 1 over n squared, or
No.
change that somehow?
This is merely an argument that's inconclusive in determining whether or not the series converges or diverges. That's all I was
So,
suggesting.
can we change the right-hand side in any way to make it either conclusive or, make it conclusive?
Yeah, I did. That's why I changed it the first time. For having Korean in.
Can we change the one we made up, on the,
Oh, are you suggesting, can I compare it to something else?
yeah.
And get a conclusive answer.
Not very easily, not in this example, no way. Because of the algebraic structure of both my numerator and denominator. Nothing I can see, absolutely not.
How do we
So-
know that, how can we tell if we picked the right number to compare it to, or it's just inconclusive?
Boy, I suppose you can look ahead, and that's how I create these examples out of thin air, if you're familiar enough with series. But on your own, just ask yourself. If everything's all positive, am I not going to compare it to something like smaller n squared? But since these two terms are positive, getting rid of them, the inequality should go in the other direction.
So what would you do if you couldn't use the limit
All right,
comparison?
when
Would
the
you
very
just-
first example, he's got a good point. I never finished my question, did I? I asked, does the series converge or diverge? I didn't finish because I was addressing the issue of giving an example of comparison. But now that the comparison test failed, but it came so close, you guys, my fist. Limit comparison to what? To what? Yeah, what I just came up with down here, 1 over n squared. By the way, can you do it in your head? What happens?
Oh, just n to the fourth.
Boy, in your head, limit is any increased step bound of my nth term over that nth term. You invert and multiply. Don't you get basically n to the fourth over n to the fourth? Isn't that limit clearly 1? Therefore, the limit comparison test says my particular series does the same thing as a series whose n term is over there, but that's the nth term of a series that converges as a p series with p being equal to 2, which is bigger than 1. Therefore, my series converges as well. You guys yell at me if I'm talking too fast.
Right, but if you did
Yes.
if you did a limit comparison test with 1 over n cubed, then you would get.
I get infinity, which I think the limit comparison test is a conclusive one. Because I want this to be equal to L, which is strictly positive. Although I admit infinity is okay, as long as what I compare it to diverges and it doesn't.
Okay, so if we do the limit, we get like n to that solution.
Or 0.
Or 0. We need to maybe rethink our choice and what we're comparing it to.
Maybe. I think getting 0 with the limit comparison test is fine as long as I was comparing to converge. Then I converge is fine. But if you get infinity with that limit, then if what I'm comparing to diverges, then I know I diverge as well. Remember those two special cases at the end of the limit comparison test? But I admit, if you get infinity, and what you're comparing to converges, or if you get 0, and what you're comparing to diverges, it's synchronized. Better?
Yep.
Who's the first person, really, who came with the idea of just honing in on how accurate this approximation is? Oh, well before that. Of course, Archimedes. He was walking along at around, what, when did he die? 260 BC, I think, something like that. And by the time he was walking around, the Egyptians had a pretty decent approximation for pi. I think something like that. But you know, the question is, so what? How accurate is it? And no one knew. Well, in terms of details. And so he decided he was going to look at computing the circumference of a circle, because if he can compute the circumference, all he has to do is divide that by the diameter, he's got pi. And so he decided to get an approximation for the circumference of the circle by inscribing a square, which, by the way, was a miserable approximation. So he decided to double the number of sides, because he can compute the perimeter of this regular agon, this octagon. Computed the perimeter, got a better approximation for the circumference of the circle, divide by the diameter, get a better approximation for pi. And he did it over and over and over again, increased by 2 the number of sides of those regular n-gons. He did it a lot, and came up with an approximation pi was really close, but he still had no clue how close it was. So he stopped. He said, well, let me circumscribe a square about that circle and compute its perimeter. Oh, not very close. Doubled its number of sides and repeated the process over and over and over and over again until finally got another approximation. Seemed to be really close, but what he got in green and what he got in red were upper and lower bounds that found him for the circumference of the circle, so he knew exactly how accurate he was. He knew an upper bound for how far off he was from the real value of pi. And we would do this often. We'll do it today in class, I hope. So if I've answered your question. Oh, I want to cry. class, I blink and class is over.
Let's just get into it.
Actually, can we just take a break? Can we take a break? Yeah. Graham?